go over these two announcements I think you've heard before, but in case you haven't, here they are. Let's get started from current slide. Okay. Our volleyball team, I guess this is their end of the season, because coming up Friday, Saturday, and Sunday, November 1st, 2nd, and 3rd, is the NJCAA. The only thing I can figure that stands for is National Junior College Athletic Association, District L/M, and I don't know if that's the district we're in, L and M, or if that's ladies and men, or I don't know what that stands for, but the tournament is up in Boaz, Alabama at, I guess, Snead State Community College, and that's will be going on this weekend. So if you happen to be up in the Boaz area, stop in and cheer the team to victory. And then this is an announcement that's pretty incredible. This is from a Dr. Christina N. Mora. She says she is one of the newest cohort of merit scholars at UAB. I'm not absolutely certain what that entails, but it sounds impressive. She's a postdoctoral candidate there. She came across this one-week summer opportunity for college students interested in biopharma manufacturing careers. In other words, it sounds like a career developing manufacturing drugs is what it sounds like. I don't know if that's what it is, but I think it is. And she thought one of our students may be interested. The students are paying $1,000 for 1 week, and their travel expenses are covered. So it sounds like quite a good deal coming up this summer. The application deadline is in January, but she doesn't say when. She does put a link here of a website you can go to and probably get all the information you need, or at least find out who you can ask to get more information if you need it. Sounds like a great deal if you're interested in the biopharma manufacturing career. Okay. All right. Any questions on anything we've done so far? None? Okay. Then we're in example 1 on page 567. So here is the integral they're asking us about. Okay? Find the integral of dx over x on the square root of x minus 1. Now, I don't particularly have a hankering to try to figure out what kind of technique to use to solve that. That's rather doesn't look like anything we've done. If that would have been x times x minus 1, yeah, partial fractions. It's not, okay? In the denominator, you have a bit of a mess, okay? So, where would we go in the table to look? So let's go back to the back of the book to the tables. And I think I went too far. There we are. Okay. Tables back on pages A3 through A6. Okay? And look at some of the headers here. It says forms involving u to the n, certainly not. A plus u to the A plus BU. It has a little bit of character, but not. A plus BU plus CU squared. Nope. How about this one? Forms involving the square root of A plus BU. That looks like that could be the case. So that's at the bottom of page A3. And looking down at number 17, that looks like it fits the bill. Okay? And here's what number 17 says. Okay. Is the integral, I'll get my pen set up, of 1 over u onto the square root of A plus BU. Okay. Before I go any further, let me just flip a page or two. Now that well, we'll see what we can do with it. We'll try that one first. And if that doesn't seem to work, we'll come back and try something else. And that this integral, all wrapped up in my wire here. Okay. du is equal to, and this is a two-part answer. So let's see how closely we are. So it looks like to me that we need x to be u. Okay? If x is equal to u, that works. This works. Have a little bit of fiddling to do here. Okay? But a would need to be a -1 and b 1. Agreed? If x, okay, let me write this. U is equal to x. Okay? The du works, that's dx. U works there, that's x. Here, the b is 1 and the a is -1. All right. Now, if you look at the choices you have in the back, there's one choice if a is greater than 1, another if greater than 0, in other words, positive, another if a is negative. That's what we've got, a negative. So our answer here would then be, I think I'll just go on and write it up here. 2 over, you tell me, you continue. And what's A? So that's just going to be 1. So that's just going to be a 2 there, okay? No reason to make it any more complicated than necessary. So that's, I'm going to bring down the 2 a little bit. Okay, that's 2. What's next? Inverse tangent. So tan to the -1. I like that. It's easier to write. Times the square root of, what's up top? Okay, I would write it as x minus 1. Okay, it's exactly what's under the radical there. Okay, over. Okay, a minus 1, a minus 1, it's just 1. So let's reduce that size of that radical a little bit then. Okay. Inverse tangent of x minus 1 plus c. That's it. That is it. Okay? Now, let's see if they got it to be that easy. Yep. 2 inverse tangent square root of x minus 1 plus c. Now, if you're ever in doubt, you can always go back and take a derivative of this and see if you get the antiderivative in your integrand. You should, okay? I'm not going to now. I'll leave that to the student, okay? Now, let me get something back in place here. Whoa, that was too much. Yeah, get that back in place here so we can erase what I've done. Any questions before I erase it? Merely using the tables. Okay, first thing, because the expression inside the radical is linear, you should consider forms involving square root of a plus bu. And that's formula 17, but we use the one where a is negative, because a is your -1 there. And I recommend writing those things out so it makes more sense to you. And then this is the formula 17 when a is negative. And when you deal with that, so Seems like you would have said let A equal negative 1, B equal 1, and U equal X first, and then said, so we'll use A less than 0, but they've just got it backwards. Okay, then du is dx, that's fine. You can write this as the integral of dx over x times x, exactly what our integral was, is equal to 2 over 1, which is just 2, inverse tangent of the argument that you have there over 1. So that's just the argument you have, the square root of x minus 1 plus c. So look it up, write it down, make sure all your pieces fit. Okay? Now, they're skipping example 2, example 3, before they get to reduction formulas. So let's go back. Were there any questions about example 1 before I leave it? Okay? Let's go to example 2. Now, example 2 has an advantage in that you can go to larsoncalculus.com and see an interactive version of this type of example. But let's see what we've got here. This is the integral we're looking for now, the square root of x onto the square root of x fourth minus 9 dx. Okay. Now, right off the top, that makes me think that same section we're dealing with. No, not the same section, because that was a linear form. Forms involving a plus bu. We don't have an a plus bu. We have an x fourth minus 9. Well, if you go a little further, you'll see a squared plus or minus u squared, and then you have the square root of u squared plus or minus a squared. That's getting a little closer, but those are still squares. You can scan, if you'd like, through the rest of the tables, and you don't see anything with x to the fourth, do you? Okay, so I think we're going to have to use the u squared plus or minus a squared. Okay, and the one that looks like it's going to come closest to fitting this is I'm sorry, take that back. Square root of a squared minus u squared. That looks like it's going to come closer. Yes, I think so. No, not quite. Well, we're going to have to do some maneuvering on this one, I think, for sure. Because we've got a radical there, we need either the forms involving u squared plus or minus a squared, that may work, or the square root of a squared minus u squared, which looks less likely to work. Now, the one that looks closest so far is 27. I'm not sure that's going to be the best one, but let's see what we can do. Let me make sure I've copied my problem right. I did. Okay. So let's see if 27 will come close. 27, okay, is the integral of u squared, there's a problem, times the square root of u squared plus or minus a squared. Okay. Now, my finger's getting tired of holding this in place, so I'm going to put that in there. Okay. Now, again, we don't have any that have fourths in them. So on first glance here, it looks like u has to equal x squared. Okay? Now, oh, I left off my du. 27, yeah, it's just a du out here. Okay. Now, if u is equal to x squared, what is du? Anybody? Second? It's 2x, right? 2x dx. Okay. Now that's looking a little more promising because we have an x dx, so let's divide both sides of this by 2, and now we have x dx, and that'll be du over 2. Okay? All right. I'm beginning to second guess myself here. No, those are all linear. So I don't think we can do that. Okay. Let's just see what's happening here. Okay. We don't have this form though. This is now beginning to look more like a 26 rather than a 20, whatever I said, 27. Okay? And my power is blinking in and off, and I don't know why. Sometimes I think this plug is sort of screwy. And, okay. So I think rather than 27, let's go with 26. Okay. And 26 is the square root of u squared plus or minus a squared du. Okay? Now I think we're closer to what we have here. I think anyway. What is your a here? Anybody? It's the only other thing we haven't accounted for. A down here is equal to what up here? 3. Okay? And since we have a minus there, let's just treat this only for the minus case. Okay, so let's take out the plus there. Well, let's see what 26, I forgot to write that in, tells us to do with this one when you have a minus sign. It tells you this is 1/2. I'll buy that. This is the du part down here. U times the square root of u squared, we're just going to use minus a squared, u squared minus a squared, okay? And we're just going to use the minus part here, minus a squared log of absolute value u plus the square root of u squared minus a squared. Okay. Plus c. All right. Another 10 o'clock scholar. Good. Okay. Great to have you. Okay. All right. Actually, it's a little later than 10, but anyway, we'll go with that. All right. Now, we're doing Integration by the tables. Okay, and we're doing example 2. This is on page 567 in chapter 8, integration techniques and improper integrals, 8.7, integration by tables and other integration techniques. All right, the problem we have is this one. There's nothing in the table that looks just like that. So I went with 27 because it looked sort of close, but as I started fiddling with it, I saw this was actually closer to 26. So I retreated and went back to 26. And this is what we got. Now, the differences here, this is a u squared, this is an x fourth. So the u has to be x squared. Then the du would be 2x dx. When you take the derivative of this, we have an x dx up here. That's what got us back to 26. When we divide by 2, that would give us du over 2. Okay? And with a equal 3. That was minus 3 squared. Now the 26 had plus or minus here. Since this was a minus, I took off the plus and took off the pluses when the plus minuses everywhere else. Okay. So let's see what that leads us to. Well, our form up here, we've got a du over 2, so we're going to have to take a 1/2 here, which is going to make this a 1/4. Okay? Because the way they had written it was a 1/2, but since we have a du over 2, we've got it. So now I think we can plug in what we know. Okay? It's 1/4. Open parentheses. Our u is x squared. Our radical is exactly what we've got here, x to the 4th minus 9, minus 9 times the log of u, which is x squared, plus the square root of x squared minus 9 plus c. All right. Now, a couple things to note here. Okay? One is, inside the log here, x squared is always positive. Okay? And this is a principal square root, meaning a positive square root, so that's always positive, and that's a plus. So we're going to deal with plus. Now, I didn't neglect, that wasn't a plus or minus there. That was always a plus. So we can lose the absolute value bars and put parentheses there. That's the only way I see to improve this, or I don't know if it's improving it, change it a little bit. 1/4 I'm writing the wrong line. Okay, x squared, square root of x to the 4th minus 9, minus 9 log, absolute, not absolute values, x squared plus the square root of x squared minus 9 plus c. Okay, let's see how the book did on that. Okay, 1/4 x squared on 2 square root of x 4th minus 9, minus 9 log. They still kept the absolute value bars there. I don't think that's necessary. X squared is always positive, and you're only taking the principal square root of the x squared minus 9, and that can't be, principal square roots are always positive. So either way you write it, it's fine. It doesn't hurt to have the absolute value bars in there. Does that make sense? Oh! I didn't see Tiara come in. Okay. Any questions on that? I know someone just came in. What we're using is tables at the back of the book. So I hope all of you have a book. If you don't have a book, you can get integration tables in a variety of places. You can probably get them online too. I don't know how easy they are to navigate there. I would hope they'd be fairly easy. But I know when I was in college, which was decades ago, one of my professors got a really good deal on the CRC manual. That's Chemical Rubber Company is what CRC stands for. But they, I think I've still got it down in my office, published a big, thick, on as thin a paper as I've ever seen, table for, I think it was for mathematics and physics. And it was a physics class, so I'm pretty sure physics was included. And I mean, it has every integral in the world, it seems like, in there. Pages on pages of very tiny print, very thin pages, front and back, of course, and it's an incredible resource. I'm sure that somehow that's online too. But well worth your while to have something for a reference like that. And here's Devin Todd. All right. Now we've got the majority of the class members here. We're only missing Ryan, Dawson, Jemiah, and Josh. Okay. We just finished example 2. You can watch our video of it, or you can go to larsoncalculus.com for an interactive version of that type of an example. All right. Any questions before we move to example 3? Okay. If not, let me go on and erase this. And let's do, we're doing integration by tables. No chairs, just tables. Okay. This is going to be a definite integral. So we're going to evaluate the integral from 0 to 2 of x divided by 1 plus e to the minus x squared dx. Now, frankly, on this one, this looks like something you might be able to do, say, with a substitution or two, but maybe not because of that e in there. If you let u equal, say, minus x squared, du would be minus 2x dx. There's your x dx in there, but then you would have du, or minus 1/2 du, whatever, over 1 plus e to the u. Or you could have the minus u down there if you wanted to. And that still might be a toughie to do because you don't have another e to the x in it. So therefore I say, let's go to the tables, okay? Look like there might be a few things we could do, and there probably are, but let's see what we've got in the back of the book. Okay, and again, if you just came in, these are located, and this isn't very helpful, on pages A3 through A6. There are much more extensive tables than this. But look at the headers first. Forms involving u to the n. No, this is way more complicated than that. A plus bu, nope, more complicated than that. A plus bu plus cu squared, nope, way more complicated than that. Square root, nope, no square root involved here. A squared plus or minus u squared, nope. U squared, square root of u squared plus or minus a squared, nope. Square root of a squared minus u squared, nope. Involving sines and cosine, nope. Tangent, cosecant, secant, cosecant, nope. Inverse trigonometric function, nope. Oh, we finally hit one involving e to the u. Page A6, and there's a few with e to the u's. Okay, so let's peruse these, and does anyone see one that looks the most promising? 84 seems to fit the bill. So let's write down what 84 is. This is not George Orwell's book, okay? That is the integral of 1 over 1 plus e to the u du. I'll go on and write down also what they say the answer is. That's that's u, okay, minus log of 1 plus e to the u plus c. Okay, we won't need the plus c, but I'll write it down just for completeness sake. Okay, if indeed this is going to be our choice, okay, which looked like about the only choice we had, what are going to be the component pieces? What is u going to have to be? Negative x squared. For that to fit, that's got to be a negative x squared. If you choose that, that implies that du is equal to negative 2x dx, right? Well, we have an x dx, but not a negative 2x dx, so let's divide everything by negative 2 here. Okay? And I think that will help us out there. Okay? I think that's all we have to do. There's no A's, B's, or C's in here. So I think we're ready to rumble that. So it looks like what we have is can't figure out where the best place to write this is. I'll put it up here. What we have is the an integral. I'm not going to put the limits yet. We'll wait on that for a moment. And it's going to be a minus 1/2 because of that over 2 there. Okay? And then our x dx is going to be our du. And the bottom part is 1 plus e to the u. Yeah, so we've got this. So it'll be exactly minus 1/2 of what we've got down here. Right? Except for the limits. Okay? This is a little trickier. Very much trickier. Okay? Because you have to deal with those limits. I think I can do the first one. When x is equal to 0, what's u going to be? 0. When x is equal to 2, what is u going to be? Negative 4. Now that's kind of a big boo hiss, isn't it? Why? What's wrong with that picture? Yeah, you need to flip it, and what do you do when you flip it? Negate it. Okay, remember that? All right, here it is. All right. Slowly we're getting here. Just missing Ryan, Dawson, and Josh. Okay. So this will then be 1/2, because you negate it, integral from minus 4 to 0 of du over e, 1 plus e to the u. I wrote it backwards, but it isn't going to matter because it's commutative. Okay. Now, what this is on the inside here is merely this. So what we have is a positive 1/2 times u minus log of 1 plus e to the u. You don't need the plus c, evaluated between minus 4 and 0. Okay? So this is going to be 1/2. You tell me. Okay, where'd you get negative? Oh, okay, okay. If you change the limits, you don't need to go back to x squared. If you had ignored the limits, done this, then you go back to x squared, minus x squared. But since you change the limits, you don't have to go back there. So what goes next? Plug in 0 for u. And what does that give you? Nothing. Okay, right. Okay. What? The first is 0 minus the log of 1 plus what? E to the 0 is what?
0.
Okay. 7 to the 0 is 1. Negative 4,583,000 to the 0 is 1. Anything to the 0th is 1. So what would that be?
The log of 2.
Log of 2. Okay. That's the first half. Now we plug in a minus 4 for the u. And what does that give you? But you're minusing it, so that's going to be a because it's the lower limit, it's going to be a what? Help me, somebody. I'm drowning up here. Plus 4, because it's minus a minus 4, it's plus 4. And then minus a minus log, which will be a, plus log of what? Wouldn't it be 1 plus e to the minus 4? You just plug in a minus 4 there. We've already taken care of the sign change. So let's see what this gives us. Yeah. 1/2 of the 4 is going to be 2, so I'm going to pull that on the outside. Okay, and then we're going to have a plus 1/2 the log of 1 plus e to the minus 4 minus log 2. Just rearranging it a little bit. And you could, if you wanted to, rewrite this as 2 plus 1/2 the log of 1 minus, that's a 1 plus, e to the minus 4 over 2, because that's one of the rules of logarithms. The difference of 2 log is the log of the quotient. Okay. I don't know if that's any better, but what's some good news here? I don't see any absolute value bars. Well, we didn't need it, because 1's always positive, e to the u, no matter what u is always positive. Okay? So you didn't need absolute value bars there, that's why they didn't put any there. And you don't need them anywhere down here. And this thing, even though e to the minus 4 is going very quickly to 0 for very, well, not really, it's that pretty close to 0. E to the minus 4 is close to 0. So this is close to 1/2 log of that. So anyway, I think that's what we got. Now, they may not write it in that form, but let's see how they do write it. They left the 4 inside, so they did 1/2 of 4 plus log to the log of 1 plus e to the minus 4 minus log 2, which is exactly what we got. And then they plugged in numbers and got something, plugged it on their calculators, of course, got something close to 1.66, which sounds like a reasonable answer to me. Because this thing right here is a minus 4 is a very small number, and 1 plus that very small number is still going to be less than 2. Log of a number less than 1 is going to be negative, and 1/2 of that is going to be still negative. So something subtracted from 2, 1.66, sounds pretty reasonable. I don't know that it's right. I'll let you do it on your calculators and figure that out. They do show a graph here. Let me see if I can hold the book up long enough to show. Oh, yeah, no, it won't be in here. Okay. This is example 3. That's supposedly the graph of this argument here of the integrand 1 plus e to the 1 or x over 1 plus e to the minus x squared. And at 0, that's 0, obviously, and at 2, it's somewhere up there. They say it's exactly 2. Is that right? Oh, that's interesting. That would be 2. That would be 1 plus e to the minus 4, and 2 over that. So I think they're saying that's close enough to 1 down here that that's going to be awfully close to 2. It's not exactly, but it's pretty close to it. I can't hold it up any longer. And anyway, the area under here is just looking at this, the block here, 2 by 2, would be 4. That would be the area under the whole block. This is less than that, so it's less than half that, so it's less than 2, just like we said before, 1.66. Looks like a reasonable area for that. I'm not about to hold the book up there any longer. It's too heavy. All right, so that's example 3. Any questions on that? Okay. Now let's go to reduction formulas. These can be helpful and nice and okay, or they can be a real pain in the neck or some other body part. Okay. So let's see. Several of the integrals in the integration table have the form of this. The integral of f of x is equal to some g of x plus the integral of h of x. Okay? Almost like your integration by parts, but not quite, because integration by parts, this would usually be a minus sign there. Okay? And there's no relation between these things. So, what that means is that you can integrate it once and get this. Now, when you go to integrate that, you may get another reduction formula, or this may be something you can integrate right off the top. Such integration formulas are called reduction formulas because they reduce the given integral to the sum of a function plus, hopefully, a simpler integral. Okay? Maybe one we can do, or maybe one we can reduce again until we get to one that we can do. And quite often, your trig functions will follow this kind of a pattern. Okay? But other functions do too. Okay? So let's do example 4. Find the integral of x cubed sine x. Now, looking at that, what would be your assumption of how you could actually do this one without the tables? Anything come to mind? Hint, that's a product. Well, integration technique was based on a product something. You remember?
Is it one of the trig substitutions?
Not this one. Those are usually square roots of something squared, so you could do, this is not a trig substitution. Anything come to mind? It has 2 parts to it. That didn't bring anything to mind. parts. Okay, parts is parts. Okay. What would you choose to be your U part as opposed to the dV part? Remember, that's how integration by parts goes. What would be the U part? Oh, it's a long time ago. All right. That would be the x cubed, because when you take the derivative of that, it gets simpler. On the other hand, the dV would be a sine, where when you integrate that, you get a plus or minus cosine. Well, that's no more complicated. Now, the trouble is you've got to do this several times. Once to get it down to x squared, and then the other to get down to x, and then another to get rid of the x altogether, and then finally you can integrate the whatever trig function you have. Well, that trig function is going to alternate going back and forth between sine and cosine. Every time you dV it and integrate it, it will just flip back and forth. Changing signs periodically or not, you know, that's just to throw you off, but it's all in the game there. Okay, so we could either do this as integration by parts about 3 times, or remember they had to set up a table and do that. That makes it even easier, but we're wanting to use a table in the back. So let's see what we've got back there. Okay? Now, remember we passed by one that said forms involving sine u and cosine u. That would be my first place to look. Do any of those seem like they may work here? $54 looks like it's on the nose, or somebody's nose. 54 would be this one. The integral of u to the n, that looks okay, sine u du. Okay? Got to pick a couple things. First, what would you say let u be? That's just x. That implies that du would be dx, okay? One other thing you've got to assign, n is equal to 3, okay? I can't write, okay? N's equal to 3. All right, now, so I'm all in favor of just going up to the top one, not messing with the u's. Well, we got to mess with them some. Let me write down what the u is down here. This is 54. This is equal to minus u to the n cosine u plus n times the integral of u to the n minus 1 cosine u du. You can almost see the integration by parts just right there in this. Okay, now I'm going to take that with what we've changed here and do the one up here. So what will that be? It's the integral. What's your x? Well, what would, okay. The x is the same as u, so that would be, we don't have to write that again. Let's just write the answer down. Okay, we don't need the integral anymore. Okay, let's just write down the answer with these things plugged in. What was u? Okay, here's a minus sign. X. What was n? 3. X cubed. Cosine. And what was u? X. Plus, what was n? 3 times the integral of, what was u? X. What's n minus 1? 2. Cosine. What's the u? X. And what's du? Dx. Done. except we still got an integral there. So let's go with that one. All right, for me to erase at least part of 54 here, just so it's out of our way. In fact, let me erase all this. I may come back to it if I need it. I think I might. But let's see what we got. Okay. So this is equal to minus x cubed cosine x plus 3. But here we have another integral. Now, sure enough, if I were doing this, I would do this by what method? Integrate by parts again. But since we're using the table, let's use the table.
It looks like 53.
It's what? It's exactly 53. Well, not 53. 51, isn't it? Oh, nope, not 51 either. 55, right?
Okay.
That's 55. Okay? So I'm going to sneak up here and put in 55. Okay? 55 is the integral of u to the n. Now, you don't have to do this once you get the hang of it. In fact, I'm getting sick and tired of doing it. Cosine u of u du, and we are told that is equal to u to the n sine u minus n times the integral of u to the n minus 1 sine u du. Okay. A lot like we had before, only this time it's a minus sign there. Okay. Let's figure out what's what here. What's u? From the one right above it. What's u? X. What's n? 2. What's du? Dx. Okay, that's going to be pretty easy. So let's plug in. Everywhere we see a u, we're going to write an x. So this will be 3 times, okay, you tell me. This answer here, plugging in these values here. X squared sine x minus 2 times the integral of x sine x dx. If you can read my ugly writing there. Okay? Now, let's distribute that 3 across and see what we get. So this is going to be minus x cubed cosine x plus 3x squared sine x minus 6 times the integral of x sine x dx. Did I do that right? Yeah, I guess so. Okay. Yeah. Agreed? Well, we still got an integral there, don't we, folks? Does this look like anything we see here? 52, okay? Now, I'll write it down. 52 says the integral of, this is 52, the integral of u sine u du, u sine u du. Okay, pretty obvious what's what here, right? U is equal to x, right? And even the du is equal to dx. I'm not going to write that down again, okay? And what is this equal to? 52 says it's sine u minus u cosine u plus c no more integrals. All right? So what do we have here? Our whole thing from the beginning is minus x cubed cosine x plus 3x squared sine x minus 6 times this thing. Only we're going to plug an x everywhere we see a u. So that would be what? Sine x. Whoops, sine x is not 6, okay? Okay, sine x minus what? X cosine x. And then I'm going to hold off my plus c for a moment, okay? And write down my answer as minus x cubed cosine x plus 3x squared sine x minus, I'm going to rearrange the order here slightly, okay, and make it plus 6x cosine x, and then minus 6 sine x. Now put my plus c. Okay. Quite often with these reduction formulas, you got to hang on to what you had to begin with. Don't lose it somewhere. And they string out, and string out, and string out, because you always had a function plus an integral. And then that integral had a function plus an integral. And that integral you could actually calculate. And if that was a 6c, guess what? It's still a constant. So don't put 6c, just put c. Okay. That's why I said so hang off on that for a moment. And just put whatever constant. Yeah. Let's see how we did. Okay. So back to here, example 4. Minus x cubed cosine x plus 3x squared sine x plus 6x cosine x minus 6 sine x plus c. They even did it in the same order I did. Now notice what's happening here. The reason I chose this order is my x's, x cubed, x squared, x, and x to the 0, which is 1. Notice what else? Your signs alternate. Plus, minus, oops, they don't alternate completely. Your trig functions alternate. Cosine, sine, cosine, sine. But because of the changing signs between antiderivative of sine and antiderivative of cosine, that flips the signs a little bit. So that makes this one a plus, that one a minus, and this one's a plus, and that one's a minus. The cosines alternate signs and the sines alternate signs. So it's bizarre, but true. Okay. Don't try to impose too much pattern in it, just do it. But that's what we got. Let's see how they did it. I have a feeling it's fairly similar. Any questions before I erase? Okay. Consider the 3 formulas listed below. Formula 52, which starts with no. This is the one you end with. Who would look at them in this order? Not me. Okay? Yes, that's the one I would look at first, 54. That's the one we did first. And then once we did that, that gave us a integral there with u to something times cosine. Then you would look at 55, which is your u to the something cosine. And then that finally gets you down to a u sine u. That gets you up to 52. So, wacko the way they put them here. Using 54, 55, and 52 in that order, here's what you get. Just like we did. Integral of x cubed sine x dx. 54 tells you it's x minus x cubed cosine x plus 3 times x to the minus 1 then cosine x dx. That leads you to the 55, which don't lose this one. Hang on to it. Don't forget it. 3 times, and when you do this one, you leave that as x squared, but change that to sine, minus 2, and then drop this by 1, x sine x dx, okay? Now, keep up with your parentheses too and distribute. That leads you to the minus x cubed sine x, cosine x, that's fine. The plus 3x squared sine x, that's fine. But then remember, this is a minus 6, but when you do this one, that changes to a plus, and it's plus 6x cosine x minus 6 sine x plus 6. They skipped a lot of steps there, but got the right answer. Any questions? Okay. Before we go to rational functions, we still have example 5 to do, so let's back up. Oh, another 10 o'clock scholar. Okay. Dawson's here. It's close to 11. After 11. Okay. Glad you're here, though. All right. So, I think I have more room if I back up a little further. Right there. Yeah. Let's use this space. We're in Chapter 8, Integration Techniques and Improper Integrals. In 8.7, Integration by Tables and Other Integration Techniques. And we're on page 568, which is the second example, example 5, of reduction formulas. And here's what the integral is. Oh, my word. Is find the integral of the square root of 3 minus 5x divided by 2x dx. Now, on first glance of that one, does anything come to mind? Maybe getting out of Dodge as soon as possible, okay? But don't do that, okay? Got to figure out something here, okay? One sort of weird thought would be let u substitution, u equal 3 minus 5x, and then solve that for x in terms of u, and then plug that into your denominator. But I have a feeling that would turn into a very ugly mess. So let's see if a table can help us here. Since we're in the integration by tables mode, let's see what the tables show. Now, again, it looks like we're back to the square root of linear things where we started. Now, that would be forms involving square root of a plus bu, because that's sort of what we've got here, except we've got something in the denominator, okay?
About 19.
Second?
Number 19.
19. I was just going to turn the page to see. That looks like it holds promise, doesn't it? Okay? So I think we're going to have to go with 19. So let's list what 19 is. 19 is the integral of the square root of a plus bu over u to the n. No, u. I'm looking at the wrong one. I was going to say we don't need an n there. Okay. Over u du. And it says that's equal to, believe it or not, a negative 1 over. No, that's, I'm still, my eyes keep dropping down to the next level. We don't want that. Okay? That's equal to 2, the square root of a plus bu plus a, reduction times the integral of, you knew that was going to happen, didn't you? 1 over u onto the square root of a plus bu du. Somehow, this doesn't make me feel warm and fuzzy yet, okay? But let's see what happens. Let's first see what we're going to have to let be what, okay?
A equals 3.
What's that?
A equals 3.
A is equal to C. He's got that down. A equal 3. Next. Second. B is equal to, what do you say? I couldn't hear. Oh, U equal X. Okay, U equal X. Got that. And B is equal to? -5, you said? Say yes? Okay. All right. Now, we do have to make one small modification. Anyone see what that might be?
The 2x.
Yes. Pull the 2 on the outside. Make this 1/2 of the square root of 3 minus 5x over x dx. That works much better, doesn't it? And that 2 can come outside. It wasn't in a radical or any other way messed up. And of course, what's your dx? If u is equal to x, your du is equal to dx as well. So du equal dx. Okay, if I could write. Okay, so let's plug in our answer. Don't forget that 1/2. So here's the 1/2. Now, what we have here is this with these substitutions in. So how does that start? 2. That's pretty handy, isn't it? Because we're going to cancel out in just a minute. Now, rather than plugging away, this thing right here, the a plus bu is exactly your square root, is exactly your 3 minus 5x. So just write it down. The square root of 3 minus 5x. You don't have to do each one. That's exactly that. Okay? Plus, what's your a? 3, okay, times the integral of, I'm going to put dx up here. Is that okay? What's in the bottom? Denominator, x times the square root of 3 minus 5x. Okay. Now, going to take the first term there, that first function, and I'm going to do exactly what I said I was going to do. I'm going to divide out the 2's. So that's going to be the square root of 3 minus 5x. Okay? And then it's going to be plus a 3/2. Remember that half distributes across there too. That integral. Now, we've got to figure out what that integral is. Okay? I bet you it's in the same section, but maybe flip back a page. Which number now? By the way, we're using the tables at the end, the integration tables in Appendix B, but it's on page A, 3, 4, 5, and 6.
17.
That's number 17. So 17 tells us that the integral of 1 over, I'm going to put du over because I don't have enough room to write the 1, u square root of a plus bu, u times the square root of a plus bu. Okay? Now guess what? Your u's are the same, your a's the same, your b's the same. And what does this tell you that is equal to? Oh, that's the one, remember, we used before. But this time the a is positive. So we use the upper one here, right? This will be 1 over the square root of a times the natural log of absolute value of the square root of a plus BU. My A's and U's are beginning to look a lot alike. Minus root A over the square root of A plus BU plus root A. And then we have our plus C. Okay? So, remember your 3/2 is in front of all that. So let's write that in. What is the first step here? 1 over root A would be 1 over root 3. Okay? Times the natural log of, and this thing in the parenthesis, in the radical is exactly what you have here, the square root of 3 minus 5x, okay, minus root 3, right, over the square root of 3 minus 5x plus root 3. All right. And then you have your plus C. Don't forget your plus C. I didn't have room to write it on the right. So what's our final answer? Or almost our final answer? It will be, I think. The square root of 3 minus 5x. Okay, that comes out. Now, I really don't like too much having that root 3 in the denominator there, though it doesn't bother me big time. But you see, you can divide that into 3, and what would you have? Root 3. Root 3 over 2 times the natural log of absolute value root 3 minus 5x minus root 3 over the square root of root 3 minus 5x plus root 3. Plus C. That's what I hope our answer is. Let's go back and see. Okay, what we got here. Square root of 3 minus 5x plus root 3 over 2, they did it right, log of the square root of root 3 minus 5x minus 3, root 3 over the square root of root 3 minus 5x plus root 3 plus C. Excellent. Way to go. Any questions? I'm glad we have the tables for ones like that. Like I said, there would have been a couple of ways you might could have launched it, but you probably would have come and said, no, let's not do that. Let's try this. Let's try that. This just gives it to you. It's rather long and involved this way, but this is shorter than digging it through it yourself most of the time. All right. Any questions on that then? All right. Let's move on to rational functions of sine and cosine. Now we've done integrating trigonometric functions, trig substitution. We've done lots of things, but we hadn't done any of the rational functions of sine and cosine. What in the world do we mean by that? Well, here's the first example. Find the integral of sine of 2x over 2 plus cosine x dx. Okay. First inclination, or do you have any inclination? And don't flee the coop. Okay. That's not what we mean. What would you think? Jump to the table? Let's do it. And see if the tables are at all helpful here. Okay? Now that would certainly be involving sine and cosine. That would be 46 through 58. Okay? Do you see anything that looks remotely like this? And if not, what's the big problem? The biggest problem. There may be several problems here. What's the biggest one? Anybody? When you first look at that, does anything bother you about it?
The
Two different arguments of your trig function. One's a sine 2x and the other's a cosine x. Nothing in the table has multiple arguments of that. So what would you suggest that we do here? I'm going to have to talk to some trig instructors, I think. I'll be talking to myself on a lot of you here. Now let's see. I can't remember. Yes. Your front inside cover, this page that's perforated, mine's about to come out. That has your trigonometric identities. And let's see if we have one that says anything like sine 2x. Anyone remember that? Or can look it up and see it? So you're going from the back of your book to the table, to the front of your book to your inside cover. Anybody? Second? That's it. 2 sine x cosine x. Okay? So I'm going to pull the 2 on the outside and make this sine x cosine x over 2 plus cosine x and then have a dx. Okay? Now, I go back to the back of the book, and am I any better off? Apparently not. Okay? Unless, of course, I'm not much better off at all. I was going to say I have a suggestion here what we could do, but that doesn't really seem to be very helpful here either. Now, I'll tell you the next thing that comes to mind when I look here and I don't see anything that looks all that promising. The thing that comes closest is number 57, but that's with a 1 in the numerator. And that's not particularly, that doesn't make me feel warm and fuzzy. Okay? Now, does anyone remember kind of a trick of what you do when you have, especially a binomial involving a sine or a cosine in your denominator? I don't know if this is where the book's heading, but I'm going to tell you my thoughts on it.
It's not division, is it?
No, that's a decent thought, but well, it doesn't feel warm and fuzzy to me right now. Here's what does. Have y'all heard this before? Multiply by the what?
Are you multiplying the numerator and the denominator by the denominator?
Not by the denominator, close to it though. The what? The conjugate of the denominator. What would that be? 2 minus cosine x. Now I still don't feel totally warm and fuzzy with this one because I'm afraid something is not going to work out too well here either, but let's try it. What does that get? Again, you know, this is, okay, the 2, don't forget your 2, you pulled that out. Okay, now what you have, let's do the denominator first. What does that give us? Anybody? This is not feeling warm and fuzzy. What does that give you? 4 minus cosine squared x. That's what you said, right?
Yes.
Yeah, I thought you did. Okay. Now, if that was a 1 minus cosine squared x, I would really feel good about it. It's not. It's 4 minus that. So now that's what leads me to think maybe that's not such a good idea. Okay? So rather than waste too much class time, because we are sort of running short of class time, let me glance up here and do a shortcut here. First step we did exactly as we said. Okay. Not what we did the second. The first step was perfectly fine. The second step was where we messed up, or where I messed up. Okay, so let's go back to what we had here. Okay. And it's a little bit of a trick here, but you know, after a while, you start learning tricks, okay? I'm not going to say doing tricks, that doesn't have the right connotation, but anyway. Now, what two functions are you dealing with? Sine and cosine. Are they related in any way? Especially in a derivative integral type sense. How? I'll only do it the other way. And besides, you had it wrong, but yeah, okay. Yeah, okay. Since cosine shows up the most, let's let u equal cosine x. Then, what? du is equal to negative sine x dx. Ha! This may be getting somewhere. Maybe. Let's see. Don't forget the 2. That's out front there. And your integral now is, I'm going to bring a minus out with the 2 because we don't have a minus sine x dx. We have a sine x dx. So let's move the minus over there. So bring that out front. And what we have now is a u, that's cosine x, du, that's the sine x dx, that's this part, over 2 plus u. Me? Yeah, okay. Now, that's one that maybe we should go back and look at the table. Forget the sines and cosine, let's go back to that. And that is a linear form, forms involving a plus bu. Okay? And what is the first one you see there? Number 3. And what does that tell you? This will be, number 3 is the integral of u over a plus bu du is equal to 1 over b squared. What do these long ones always wind up against the margin? Bu minus a log, absolute value, a plus bu, and then we have a plus c somewhere out there. Okay. What's going to be our representations here? Oh, sorry about that. We got u's equals u's, okay. U is u, okay? You don't change, okay. What else do we have? A is equal to 2 and b is equal to 1. Okay, that's going to make some of this a lot easier. All right, so we have a minus 2 out front, and this integral right here, with these things substituted in, yields this. So what is that going to be? One over b squared is going to be 1. Okay, I got that. And then what we have after that?
Cosine x minus 2.
Okay, it's, okay, you're going on and plugging in. I was just going to do this. Yeah, it's fine. Okay, but just to keep it. U minus 2 times the log of absolute value, and that A plus BU is exactly your 2 plus U, okay, plus C, okay. I'm going to block off and leave the C on the outside. Now, I think what you were doing was quite nice. Negative 2, and what's your U? Cosine X. Now, negative 2 times negative 2 is plus 4 times the log of, and this 2 plus U, I think, is exactly your 2 plus cosine X plus C. Now, I think we may be getting a little rain. Okay. What's one thing you notice you might be able to do? Lose the absolute value stuff. Why? How can you say that? Cosine goes negative, doesn't it? But what's the most negative it ever goes?
It can't be greater, or it can't be less than negative 1.
Exactly. So the least this could be would be a 1. Okay? So you don't need the absolute values there. So I would write this as, I think I'd rearrange it and write it 4 log 2 plus cosine x minus 2 cosine x plus c. Let's see how they did it. Okay? Oh, we got it here, but we'll do it. They left the minus 2 cosine x in front, plus 2. They left the absolute value bars there, unnecessary, but it's okay. It doesn't hurt. All right. So the key there was, once you used your trig identity to get them all into the same things, then when you couldn't see anything in the table that would relate, say, wait a minute. You got sines and cosines. You got cosine twice, and derivative of cosine is related to sine. So yeah, you got a U substitution. And then the U substitution went really well with the U's in the back of the book. All right, but that wasn't why we did it, was it? Okay. So let's see how they did that. We're beginning to run low of time. Let's see how they did. Substituting 2 sine x cosine x for sine 2x, exactly as you found it. We get that, and they pulled the 2 out front, which is a good idea. And now you note that the check of the forms involving sines and cosines and appendix D says nothing looks like that. Okay? Nothing. So what you have to do is step back, get a bigger view, don't lose the forest for the trees here, and say, well, wait a minute, a U substitution would work. No, I don't first consider forms involving that. I would consider a U substitution first, and then get it into a form involving that and say, ah, this fits perfectly here. I guess in the back of their mind they did a U substitution, but they have a strange back mind, you know. First do a U substitution, and then you get it in a form that looks like this, and then you do that. I don't like the way he's presenting it. But if this is how you think, weird but fine, it's fine to think that way, okay? And A is equal to, B is equal to 1, and U is equal to cosine x. So they did the U substitution at the same time, which you also say du is equal to minus sine x dx, so then you have, yeah. This would have been my first step, okay? Rather than thinking of the table, do this first, and then you get it into the form that you saw before. If this is how you think, my goodness, go with this, is correct. But if it's not how you think, I think the way we did it was a little more logical. Okay. And anyway, that's their answer. -2 cosine x plus 4 log of, you don't need the absolute value, 2 plus cosine x plus c. All right, any questions? Okay, do we have time? Yeah, I think so, don't we? Now, substitution for rational functions of sines and cosines. For integrals involving rational functions of sines and cosines, here's a substitution you can use. Yeah, right, I know that one, don't you? I would say no. Where in the world did this come from? Does anyone? Well, maybe they did. The half-angle formula, maybe it did show up that way. In fact, I think it showed up about 3 different ways. And that is one of the ways. Okay, so I'm sorry I was making fun of it, but that's not one that is on the top of my brain. But you got that front and side cover of your book, so use it. Cosine. Whoa. For integrals involving rational functions sine and cosine, the substitution u is equal to that. Frankly, I'd never think of that as a substitution. Okay, I just wouldn't do it. That this is equal to that, I can see. I mean, you can look that up at a table. Yeah, I remember that. But then to let u be that, I'm not sure. And then to say, then yields this. And I'm not sure that's intuitively obvious. I'm sure it's correct, but it certainly isn't intuitively obvious. Okay? Sine would then be this. And dx would be that. I would say, what planet are you from? These things are not at all. Oh, yes, of course. You know, where did that come from? Okay. Wow. You can work through it and see it's all true, every bit of it, but that's not a substitution that would ever pop into my brain. Ever. But they say you can use them, and indeed you can. Now, they do have one of those QR codes, isn't that what you call them? Perhaps going to that, they'll give a little better explanation. But they don't even have you do a problem with it. Now, they do the proof, which I think is nice to do, to show you take that first one, square this, and square that, which of course would be squaring that, but you never use that. So anyway, that would be sine squared, and then this gets really complicated in the denominator, and then you do 1 minus that and a 1 plus that, and you wind up finding out that winds up being cosine. Now that is not how I would ever have done the problem. Now we may get the same way, but here's how, if I had this form, sine x over 1 plus cosine x. This goes back to what I was going to have you do before, but it didn't work on the last problem. Multiply numerator and denominator by the conjugate. It works well when it's a 1 there. It doesn't work when it's a 2 or a 4 or something else, okay? And multiply this by 1 minus cosine x. You have to multiply the same thing by both. This gives you sine x times 1 minus cosine x over 1 minus cosine squared x, and this is sine x times 1 minus cosine x over sine squared x, which gives you that. Okay? I'm not sure that gets you anywhere in particular. It just gives you another form for u. Okay? So maybe that wouldn't have been helpful at all. I don't know. They do that right at the end, don't give you a single problem with it. I say don't worry with it. Okay. 8.7. Do number 3. It's a Calc Chat and Calc View. Number 5 is a Calc Chat. 7 and 9 are at Calc Chat. 11 is a Calc Chat. 13 is a Calc Chat. 15 and 17 are both a Calc Chat. 15 is a Calc View. Any of the odds 19 to 39 are all at Calc Chat. 41 to, odds 41 to 47 are at Calc Chat. 41 is at Calc View. 49 to 53 are at Calc Chat only, okay, and 55 through 61 are at Calc Chat. 63 is at Calc Chat. 65, you can look into that if you're interested. 67 and 69 and 71 are all applied problems using this. So I would say do one or more of those. They should all be at Calc Chat. Now, we're not going to do improper integrals. And Devin, I wish you hadn't left yet. Is he gone completely? Because I wanted to give y'all a present because you've been such nice students all week this week. And that was going to be your test on chapter. Okay, where is it? I ran it off. Oh, I'm in the wrong class. Okay, here we go. Here's test 2. Does any of you going to see Devin? You want Devin that well?
If I see the bottom.
Huh?
If I see the bottom.
You think so? You want to give him one?
Sure, I'll get some.
Okay. If not, bring it back. Now, will anyone see Josh? You will? Okay. And who else will we mention? One more. Ryan. Anyone see Ryan?
I'll see.
Well, you'll see him more. All right. Got rid of all that. Okay. Good deal. Because we're going to just have a slideshow on, I've got everything out of order, on 8.8. And that's the end of the chapter. So if you want some more exercises to work on, review exercises at the back. 1 through 7 are, this is on page 583, they're at Calc Chat. 9 through 15 are at Calc Chat. 17 through 25 are at Calc Chat. 27 is at Calc Chat. 29 through 33, 35, 37 to 43, 45 or 47, 49 through 55, 57 to 63, 65 or 67, 69 through 73, 75, 77, 79 through 85, and then, oh wait, some of those are empty. Okay. Stop when you get to 77. Okay. I don't think you need to do any past that. All right. Good deal. There is a problem-solving thing, and that's all. Okay. So we'll just do a slideshow on 8.8, improper integrals, just in case you ever need it, but I wasn't going to test you on it. And then we'll move, Chapter 9 is infinite series. We're only going to do 9.1 and 9.2, and then we'll move into Chapter 10. So the next test will cover 9, 10, and as much as we get covered in 11. Good deal.